All right. Ooh, there we go. So due to a bit of laziness and mix-up on my part, we have the unstyled version of my presentation today. So about half the slides are going to have styling, and most of the actual meat of the subject won't. My name is James Prestwich. I've been involved in crypto for about 7, almost 8 years now. So when I started, there wasn't Ethereum as a thing. There was Bitcoin and the Bitcoin imitators. And that's really all there was. I got started in crypto by founding a decentralized storage company back in 2014-ish. So what I work on all day now is cross-chain communication protocols. I had a company called Summa from 2018 to 2020. We were acquired by C Labs, and I work at C Labs on Celo. We build a proof-of-stake EVM chain, and I lead the bridges team working on cross-chain communication protocols. So the talk today is a bit about what is a bridge, what is cross-chain communication, and what's the design space for these things. When we're talking about bridging tokens from Ethereum to Celo or to Matic or anywhere else, what kinds of decisions do we have to make about the bridge in order to achieve this? And what are the different trade-offs between all the types of bridges out there? So we're going to go real quickly. What is a bridge? Some cross-chain communication terminology that you'll need to know. And then we're going to just dive into what are the trade-offs of all these applications. I'm going to be taking breaks throughout the talk for questions. I tend to cover really a lot of material very quickly, and I want to make sure that everyone kind of stays on the same page as me. So every few minutes, I'm going to stop and see if anyone has questions. Feel free to raise your hand, and I think a couple people with microphones are walking around. All right, so what's a bridge? When we're talking about bridging chains or DeFi bridges, we're talking about an application. We're not talking about a base technology. We're talking about something that serves a user need. We use cross-chain communication channels to build bridges. Bridges aren't the only thing you can do with cross-chain communication channels. And there are a bunch of different choices of channel technology you can use to build bridges. And the goal of a bridge as an application is to represent tokens from another chain. So to represent Ether on Celo, or to represent the Uniswap token on Ether or Solana or Near or anywhere else in the ecosystem. Putting it all together, a bridge is an application that uses cross-chain communication to represent tokens from another chain. And the goal is to use your Celo in Ethereum DeFi or vice versa. Okay, so glossary. It gets very difficult to talk about anything in a cross-chain environment. We can't just say on-chain. We can't just say it's an ERC20 token. So we have some pretty specific terminology that I'm going to go over pretty quickly. When we're talking about bridges, we have to talk about where we're bridging from and where we're bridging to. And we call these domains. We don't usually say we're bridging between chains because we actually build bridges not just between layer 1s, but between layer 1s and layer 2. So if you want to move your Ether from Ethereum to Optimism, you need to use the Optimism bridge. If you want to move your Ether onto ZK Sync, you need to use the ZK Sync bridge. So we want to talk about domains rather than chains because not everything's a chain. IBC is very particular about this because their concept of a bridge includes completely trusted proof of authority databases. So the next piece of terminology is where is the action taking place? In the context of a domain, we have things running in Celo, and a contract in Celo can talk to them directly. So those things are local. Things that are on Ethereum can't be directly communicated with from Celo, so those are remote, and we need to handle them differently. We use channels to connect and communicate with remote contracts, remote assets, remote users, anything that's in another domain. So when you move your Ether from Optimism back to mainnet, you use a channel to send a message from the Optimism chain to the Ethereum chain. We use channels to connect those two domains. And in the context of a domain, tokens, the thing we want to bridge, are either locally or remotely originating. On Celo, Ether is a remote asset. It exists, it's defined by some other domain. We don't know anything about it. It could be anything, but Celo needs to make a representation of that remote asset. We need a local token on Celo that represents the remotely originating asset. And that's what really defines a bridge. So this is about the point where I should stop for questions. Does anyone have questions about terminology or what a bridge is or what the goals are? I can't really see the audience from up here, so Any questions? I think we're okay. Cool. I'm going to assume that everyone understands this perfectly, and I can do the remainder of the talk at double speed. All right. So we talked a lot about a channel. Channel is how you send messages between two domains. So if you need to communicate from Ethereum to Near, you're going to use a communication channel. There are a bunch of different choices of technology for this. We've been working on different versions of this for like 3 to 4 or 5 years now. And they all have different properties, different trade-offs. They send messages in different ways. So some of the ones we worry about a lot are latency. When I send a message, how long does it take to get there? Security, how confident is the destination domain that the message it receives is valid? We can talk about this a lot more, but essentially we want to talk about is fraud possible? Who could commit fraud? Who could cause invalid messages to be processed on the remote domain? We also think a lot about implementation complexity. So some channels are extremely simple and take like 3 weeks to stand up and you can do whatever you want. Some take like 2 to 3 years to implement. Some of you may have heard of IBC back in like 2015. That's just rolling out earlier this year. We also want to worry about channel overhead. What is the cost to the chain and to the users of the chain or domain to validate messages? How much gas do we have to spend to build a channel and to keep it running? For example, I wrote a lot of code for TBTC. It uses a header relay from Bitcoin to communicate between Bitcoin and Ethereum. And that header relay costs something like $15,000 a month to operate. It was like 5 times more than that a few months ago when Ether was higher. So we want to think about, for any given channel tech, what is the cost to operate it on a given domain? And then we also have to think about reusability. When we build a channel and we spend 6 months to 3 years building it, how many domains can it reach? Most channels are designed to go from one specific domain to one other domain. The ideal is that we build some sort of channel that works for all domains. Okay, so for specific examples, IBC, which I've mentioned a few times, has very low latency. It only takes a few seconds to pass a message between two domains. And it has very high security. As long as the sending domain isn't compromised, as long as the validators haven't committed fraud, IBC will only pass valid messages. Unfortunately, IBC has very high complexity. It's been under development and in specification for years, and we've just seen it hit mainnet in the last few months. It has kind of mid overhead. You have to process all the headers from the remote chain. So there's a significant cost to different Cosmos zones to connect to IBC. And it has high reusability as long as you really like Cosmos. Once you get out of Cosmos, all of the work done for IBC needs to be redone. So we can't use IBC in Ethereum, Celo, Optimism, Near, Solana, or any other interesting domains. But you can use it as much as you want very easily within Cosmos. Optimistic rollup channels are designed specifically for connecting mainnet to the rollup. They're usually orchestrated by a contract on the mainnet. They have very good security because the mainnet is handling everything. So Ethereum handles all communication over the Optimism channel. And because they're part of a rollup, they have very high complexity. They have relatively low, like medium overhead, especially compared to a header relay like IBC or TBTC. But they're only applicable to the specific rollup that they're connected to. Arbitrum can't reuse the Optimism work, and vice versa. We end up developing a completely bespoke channel every time we build one of these. One of the most popular models for bridging that's used by like Matic and BSC and basically every other chain right now is a trusted channel. What if we just hand the money to some trusted custodian and have them hold on to it for us? These have very low latency because the custodian just gets the money and does whatever they want with it. They have no security. The custodian can cause any message to be received by the remote chain. So the custodian could run off with all of the money, cause any smart contract to receive messages that were never sent, whatever they want to do. But they are very cheap to operate and very cheap to implement, which is why they get built so often. And they're very reusable because just having some guy sign messages works everywhere. So what my team works on is the optics channels, which we trade off a bit of security and latency for lower complexity and high reusability. So optics channels permit fraudulent messages in edge cases only if everything else is falling down. And as a benefit of choosing to allow that, we are extremely cheap to run, have very low overhead, and can be used in any domain that supports basic smart contracts. The interesting thing about all these channel choices is that the bridge doesn't really, the bridge as an application just needs one of them, any one. So we talk about the trade-offs of the different channels and how they bubble up to the bridge as an application, but generally speaking, any of these choices will work for a bridge. So I'm going to ask myself a question, which I already spoiled. Can you have it all? Can you have low overhead, low complexity, high reusability? No, you can't. The rules of blockchains forbid that, and I'm happy to explain in depth why sometime after the talk. So before we get into talking about bridge trade-offs, I should pause for questions again. I'm going to back up slides a few bit to give ourselves some context. I'm happy to answer questions about channel technology.
Okay, what is it that prevents IBC from connecting with non-Cosmos chains?
IBC is an example of a header relay. So the way IBC works under the hood is that it takes the headers from the other chain and verifies them within the local chain. So the way a header is verified is specific to the Tendermint PBFT consensus proof of stake protocol that they use. And you can't reuse the header verification for other chains. Celo, ETH2, Solana, Near, they all have different headers, different consensus protocols. In order to connect to IBC, you would have to rewrite the entire header chain validation logic, which is what takes years.
Thank you.
And question,
Yeah, go ahead.
I don't know who has the mic.
Sorry.
I was just wondering if you could talk us through the thought process of picking the constraints, because I know it's never easy. And I'm just curious about how you got to where you got and what were different discussions.
A lot of these are targeting specific applications. We talk about latency because users don't want to wait 7 days for the optimism bridge to work. They have to, but they don't want to. We talk about security because we are fundamentally uncomfortable with the idea of a centralized custodian holding all the money. Complexity is because we have been waiting so long for IBC. IBC is incredible. It just arrived 3 years after we wanted to use it. And I'm going to use it in the future, but each new chain that we connect to IBC is going to take a 6-month plus process to re-implement a significant chunk of the logic. Overhead is because for TBTC, we ended up spending hundreds of thousands of dollars we didn't want to. So I think about that one an awful lot. And reusability is because I implemented the core TBTC logic for 5 different chains. And I spent a huge amount of time doing that. And I thought it would be really, really nice if I didn't have to do that for each chain each time. So the constraints are mostly from experience with specific applications. I'm not going to argue that these are the ideal set of constraints for channel tech, but they are like what we've bumped into in practice.
Can you explain? Can you explain a little bit more in depth how the optics bridging technology works?
Yeah, so we should probably say channel technology. The main thing that it does is it has an optimistic model for cross-chain communication. Really optimistic-ish. Optics guarantees that Optics designates an attester, and they regularly attest to the state of one of the chains. If the attester commits fraud, there's a waiting period which allows anyone to shut down the channel. And fraud is always detectable on the chain that sends messages. So in the edge case where the updater commits fraud and nobody closes the channel, a fraudulent message can be passed.
I'll come up and then...
We think that that should be extremely rare in practice, but we do very directly point out that this is a security trade-off. IBC permits fraudulent messages, Optics permits fraudulent messages where IBC never will. Any other questions before I move on? I think we're okay. All right, so I'm gonna fast forward back through these. You can't have it all. So bridge trade-offs. It's sometimes difficult to talk about bridges as their own application because they get conflated with the channel so often. In the history of bridging, we've actually never had a meaningful separation here. IBC has its own bridge as part of the specification. Optics is going to have a bridge that is loosely coupled. I'll come back to that in a second. All of the trusted channels are bridges and bridges only, because that's the main application that people are interested in. And there are other channels that exist, but they pretty much only get used for bridging. So we tend to conflate bridges and channels when we should really think about them as two separate things. So we have to talk about, for the bridge application, what happens if the underlying channel fails? For IBC, what if there's a liveness violation? For a trusted channel for optics, what if a fraudulent message is received? Do users lose funds? Are there any inaccessible funds? And are the representation tokens on the remote chain worthless now? We also have to talk about recovery. Can the bridge gracefully handle recovery of a failed channel? And how does it do that? How do we recover funds? How do we hook up the new channel? And how does it manage its known channels? How does the bridge become aware of an inbound channel and know that it ought to process messages coming in over that channel? What sort of permissioning aspects does a bridge have? Who gets to decide what new domains are added? What requirements are there for new domains? And who registers these on the bridge application on each domain? If we want to bridge Celo and Ethereum, the bridge application on Celo has to be aware of the bridge application on Ethereum and vice versa. What are the permissioning and ACL setups around access to those smart contract calls? We also have to think about routing. We're connecting different domains. Maybe not all domains are directly connected, and we have to send a message that passes over 2 or more channels before it reaches its destination. IBC does this very well. We have to develop some sort of identification system for domains. This is broadly similar to routing in the internet. We're making multiple hops through different routers. One of the really interesting non-intuitive questions we have is, are tokens with different routing histories fungible? So if Ether goes to Celo and then Solana, and other Ether goes directly to Solana, are those two different Ether tokens interchangeable? The technical answer is no. Because each of the tokens has to retrace its steps to get back to Ethereum. So one of them is exposed to 2 different channels, and one is exposed only to the direct channel. So the bridge application has to either expose this and make them non-fungible, or handle it somehow and make them fungible. IBC, for example, chooses to have each of these tokens be non-fungible. A token in a given domain commits to its routing history and is not fungible with the same token if it came by a different route. So again, we're going to go through examples in the wild. IBC, the IBC bridge is essentially specified alongside the IBC channels, and it only uses the IBC channels. I think they have plans to upgrade it to allow different kinds of channels, but there's no ETA on that. There's no active development. IBC bridges permit theft on channel failure. So if your tokens have passed through a domain and that domain's validator set fails, for example, those tokens can be stolen. When an IBC channel fails, it requires a public recovery process. IBC channels, like all cross-domain communication, has a trusted setup. IBC, fortunately, allows anyone to observe and verify that the setup was done correctly, which is why we call it a public recovery process. IBC has completely permissionless membership. anyone can boot up an IBC compatible chain and connect to any other domain that's IBC compatible anytime they want to. So you can boot up a single Cosmos zone, a single node Cosmos zone at home and connect directly to the Cosmos hub. And this is why IBC bridge tokens with different routing histories are not fungible, is to preserve the permissionless element. There's an inherent trade-off there. And IBC supports arbitrary routing on a graph. So you can send messages from domain to domain to domain in any number of hops. Optimistic rollups are, again, very application specific. They're designed specifically to get Ether from mainnet to the rollup. On failure, there's no theft unless the rollup itself has failed. Usually, this just results in a 7-day delay. The edge case is that the rollup fails and nobody notifies the main chain. That's probably never going to happen. Rollups require a public setup as well. So if they fail, there's a public recovery process. They can only connect 2 domains, the rollup and its host chain, and so routing is not really applicable here. Oops. So for a trusted bridge, these are bridges using trusted channels. There can be theft anytime. There is no public recovery process. There's no way that a third party can verify that the channel is set up correctly because it's running trusted code on trusted hardware. Obviously, it's permission membership, and I'm not sure if routing even makes sense in this context, because if you're having someone just hold all the money for you, you might as well go direct. Optics Bridge, the design that we're working on, is mostly implemented. We took a lot of effort to be flexible with our channel technology. So the Optics Bridge application can use any channel. It could use a trusted channel, it could use IBC, it could use any of them. And we did this deliberately to separate the logic of the communication from the logic of the application. We are going to launch using optics channels. However, we are optimistic that we can switch in the future. And if we deploy on an optimistic rollup, we're likely to use the optimistic rollup channels as well, alongside the optics channels. The optics bridge does permit theft because optics channels and other kinds of channels can process fraudulent messages. So if the channel fails, some value may be lost. Optics channels and the optics bridge have a public setup process. Anyone can verify that it was done correctly and that it's using channels that are known to be good. We have permissioned membership, and we haven't decided how it will be governed yet. We're open to suggestions there. And because optics channels have a cool one-to-many property, we require direct connection. We kind of forbid routing. We always want to be able to reach the destination in one hop. The goal there is that we can provide fungibility across all domains regardless of routing. This is getting to the end of my prepared material. I think, oh, do I have more slides? Oh, okay. So I want to talk for a minute about why these choices specifically. We chose to make flexible channels so that we could upgrade to future technology. If IBC becomes available on Celo or on Ethereum, we want to be able to use it. It has lower latency and higher security. We'd love to use it if it's available. We choose to allow theft on channel failure because some channels allow that, and we want to be abstract across all channels. We want to allow the operators of this application to choose their channel tech. We love public recovery. We love allowing users to verify that the thing is working correctly. And we've taken a lot of pains with the channel technology and with the bridge application to allow that. We've decided to go with permission membership for a very specific purpose. If we are sure that all channels are high quality, we can make tokens fungible without worry about routing. If we know that the channels won't fail, we know that we won't experience theft, and we think that having permissioned access, permissioned membership in this bridge and limiting it to high-quality domains can achieve that. Right now, in the wild, we're seeing fragmentation of USDC and other stablecoins on different chains because they have reached that chain via different bridges. We would like to have a single bridge that fixes that and has a unified representation for USDC regardless of where it came from. This is the reason that we made direct connections mandatory, is because we don't want routing to affect the token representation. Our thesis is that the representation is the most important part of the bridge application, and that unifying the representations is more important than anything else we could be doing with a bridge. So I'm James. I'm happy to take more questions. That's the actual end of my slides. Please feel free to raise your hand if you have questions. The question is, how can we make direct connection mandatory? So optics channels have an interesting property that other channel tech doesn't, which is that there's only one outbox per chain. And that outbox handles messages going to any number of remote domains. So we have this one-to-many connection just built into the channel tech. And most channel technologies can't achieve that. So because we have the ability to add connections so easily and there is already an outbox that can send to that domain, we just choose to have channels be direct all the time.
So when you say that the bridge has permission membership, do you mean that only a permission set of users can send tokens across chains?
No, we mean that only a specific set of domains or chains are participating in the bridge. We control the domains that are part of this free trade zone so that we can have a better user experience.
Come to you for permission if the code is open source.
How do we plan to enforce having domains come to us for permission if the code is open source? I think that the important thing here is the SLA that a domain can provide to the users. The code is open source and anyone could stand up their own version of this application. The representations would be fragmented and non-fungible with other versions of the application. Which of these bridges is going to provide the best SLA to users and the best user experience? I don't think that we need to force chains to come to us. I think that if we build the best representations and the most reliable system, that everyone will want to join, and it'll be good for everyone.
Makes sense.
Cool.
When you talk about reusability, you're really talking about the bridge, not the channel. Is that correct?
When I talk about reusability, I'm usually referring to the channel. For example, we've talked a lot about IBC. It works incredibly well within Tendermint. As long as you're running a Tendermint chain, IBC can get spun up and running extremely quickly. Once you get outside of Tendermint, there's no reusability right now. You can't use the same channel technology to connect Near and Ethereum without months to years of work. For a trusted channel or for an optics channel, that's not the case. The overhead to implement on the new domain is very low.
For the optics channel, like how is it low if you need to have some kind of way to do fraud proofs? Like doesn't it need to be customized to whatever the validation mechanism is?
Specifically, the latency for fraud proofs and the reusability of the code and the technology in different domains is kind of not really connected. When we talk about reusability, it's more about if I spend 1,000 developer hours building this, how many developer hours do I need to spend on the next domain? For light client-based channels, that's very high, and for trusted channels and non-light client-based, it's very low.
So is it easy to re-implement fraud proofs for different chains?
The optics channels have an interesting property, which is that the fraud proof occurs only on the sending chain. So the fraud proof occurs at the outbox for the domain rather than at the inbox for the remote domain. So we know that the fraud proofs can always be very cheaply verified at the sending domain.
Thank you.
I'm happy to answer more questions about optics channels or other cross-chain communication systems after this as well. You can find me out in the hall. Anything else right now? Great. Thanks so much. I think that's about it for me.
Okay, I'd like to thank James for the really cool insights and welcome Sonia to the stage.